Good morning, my dear students. So we are back with another class on this optics. In today's class, we will see the derivation of the relation between the object distance, image distance, and radius of curvature, and the refractive index of a spherical refracting surface. So generally, this is refraction through a spherical surface, and the surface is nothing but a convex surface when object lies in the denser medium. So what I want is you go through the note that I sent to you in the previous class, and this video will be the explanation of the derivation that we have seen before. I mean in the note that you have seen before. Okay, let us see the figure here. Let this be the refracting surface, which is denser, made of some material of higher density, mu2, surrounded by a rarer medium, mu1. This is the principal axis. So at this time, the object is going to be located. Let's take it here. The object is going to be located in the denser medium. And in the previous derivation, the object was in the rarer medium. There are two cases. One is when the object is in the rarer medium, and the second is when the object is in the denser medium. We need both the derivations in order to derive the lens maker's formula that I'll be doing in the next class. Now let this be the object. If this is the object, then let this be the ray of light coming from the object. As the light goes from denser to rarer, this will undergo refraction, and let this be the refracted ray. So when you produce this refracted ray, here image will be formed. So O is the object, I is the image. Then you need to draw one line which is perpendicular to the surface, and this line is what we call as the normal here. So this is your normal, and the normal must be passing through the center of curvature C. So generally, angle corresponding with the object we call it as alpha, angle corresponding with the image we call it as beta, and the angle corresponding with this normal we call it as gamma here. So we have got three angles, alpha, beta, gamma. And remember, the assumption will be the same. The same assumption means all these angles, alpha, beta, gamma, which are met with the principal axis, all these angles are to be treated as small. So let this point be called as A here, and this is the pole of the surface. So from here, I drop one perpendicular line on the principal axis. So let me call this as N here. Then, using Snell's law, okay, before we use Snell's law, let's identify the angle of incidence. So if this is the incident ray, and this is the normal, this angle should be the angle of incidence, I. And if this is the refracted ray must make an angle with the normal. So this angle we call as the angle of refraction, R here. So then, Snell's law says that refractive index mu, when the light travels from denser to rarer, in the figure it goes from denser to rarer. So this is the second medium, this is the first medium here. When it goes from second to first, this is equal to ratio of sine of angle of incidence to the sine of angle of refraction. This can be further written as mu 1 divided by mu 2 here. You can write like this. This is equal to sine I divided by sine R. And as all the angles are considered to be small, sine I will be taken as equivalent to simply I as sine theta. This is equivalent to theta if theta tends to 0. It means if theta is very small, sine theta is simply equal to theta here. So like this, sine R also will be equivalent to R. So if you put here, you have mu 1 by mu 2. This is equal to I by R. Or simply cross multiplication will give you mu 1 R. This is equal to mu 2 I. Let us call it as equation number 1 here. Coming to the figure, if O is the object, all the measurements to be done from the pole. So this is going to be your object distance. Since I is the image, the measurement is done from the pole. So this will be your image distance V. And since C is the center of curvature, distance between the center of curvature and the pole, which is what we call as the radius of curvature here. Okay, then our next step should be finding the values of I and R from the figure. So looking at the figure, we'll try to identify triangles with exterior angles. So if you first look at the triangle AOC, alpha is the exterior angle and the I and gamma are the interior opposite angles. So in the triangle AOC, your alpha should be equal to, the exterior angle should be equal to the sum of the opposite interior angles. So I plus gamma. This will give you I is equal to alpha minus gamma. Let us call it equation number 2 here. Okay. Then, checking one more time. Okay, it's correct. Then you have another triangle AIC. In the triangle AIC, beta will be the exterior angle and this will be the interior angle here. This and this. It means that gamma and this angle. And as we know, this angle will be equal to R here, as these two are opposite angles. So I can write this as R here. This is angle R. So looking at this triangle, in the next triangle AIC, let us call it as AIC. Beta is the exterior angle, so beta should be equal to R plus gamma. This will give you R is equal to beta minus gamma. Let us call it equation number 3. And as in the assumption, all the angles alpha, beta, gamma should be small. When you take as tan alpha should be equal to alpha. Similarly, tan beta is going to be equal to beta. It means that in place of alpha you can write tan alpha, in place of beta you can write tan beta. So putting back here, you can write I is equal to tan alpha minus tan gamma, which is equal to, in the triangle, let us find out tan alpha. Alpha is here. So this is a triangle. So height of the triangle, you can take it as AN or NA, because this is not a measurement of the object height or image height. So you can take it AN or NA, it's up to you. So you can take it as NA divided by, I am talking in this triangle here, perpendicular by base. Base should be NO followed by minus. For gamma again, then gamma will be perpendicular by base. So perpendicular you can write as Na divided by base should be N and C here. But you know that NO will be the same as PO, as P and N are very close to each other. If these two are very close, measurement of NO is equivalent to measurement of PO. So let me write as PO minus Na divided by NC. In place of NC, I can write PC. So similarly, you get it from this equation 3. So from 3 again, R is going to be 10 beta minus 10 gamma, which is equal to beta. In this triangle, perpendicular is again Na by base. Base should be Ni. So instead of Ni, you can write as Pi again, minus gamma is here. So 10 gamma is equal to, look at this triangle ANC. Perpendicular is, you can write Na again, divided by base should be NC. So instead of NC, you can write as PC, simply because P and N are very close to each other. So you can write as PC. Okay, these are the two equations we have. So you put back in equation number 1. Using in 1, you have mu1 in place of R. You can write that Na divided by Pi minus Na by PC. This is equal to mu2 I. Instead of I, you can write this, which is equal to Na by PO minus Na by PC. Na by PC. Na will cancel at one time, leaving mu1 by Pi minus mu1 by PC is equal to mu2 by PO minus mu2 by PC. Then Pi, looking at this figure Pi is equal to V. But when you apply the sign convention, if the measurement is done against the incident ray, that is taken as negative. Now let us see. In our figure, the ray travels from right to left here. As you can see, it travels in this direction, right to left. And you are going to measure as P and I here. Pi is equal to V. Since you are measuring as Pi, which is against the incident ray, so Pi will be taken as minus V. Similarly, PC. If you look at the diagram PC, the measurement is done in this direction, PC, from left to right, but the light goes from right to left. That is why PC is equal to R. This will be negative again. And PO is equal to object distance. You are measuring in the direction of PO, which is against the incident ray. That is why PO will be also taken as negative here. So put all these values here. Therefore, mu1 by, in place of Pi, I'm going to write minus V minus mu1 by, in place of PC, I'm going to write minus R. This is equal to mu2 divided by PO. PO will be written as minus U, minus mu2 by PC will be written as minus R here. So simplification will give you mu1 minus V plus mu1 by R. This is equal to minus mu2 by U plus mu2 by R here. Then let us rearrange it. We'll transfer it on the right side, and this one will bring in the left side. So, or you have mu1 minus V plus mu2 by U. This is equal to mu2 by R minus mu1 by R here. So our final equation You can construct now. Say mu1 by minus v plus mu2 by u. This is equal to, you can take it r common, so it becomes what? Mu2 minus mu1 by r here. So this is the equation that we have derived, and I hope you can understand the derivation. And for further classes, in the next class, we'll talk about the lens maker's formula. And for today, we'll stop here.